Hello, everybody. Today we will be going over the 2018 AIME I, where there are many computationally intensive problems. First, we will be looking at problem 5. And it's important to remember that in this test, or in this lecture, I'm not simply teaching you how to solve specific problems, but I'm teaching you a large class of techniques. So here we have this constraint at the top, constraining the values of x and y, and it's asking for possible values of k. So I'm going to go to my notes here, and we're going to start solving the problem. So first we have that log 2x plus y equals log 4x squared plus xy plus 7y squared. Now, if you've seen our logarithms lecture, and if you've generally solved these sorts of problems in the past, you might seem to go for the change of base formula here. But in computationally intensive tests, it's really important to save as many steps as you can. And what you can really do here is you can put both the thing on the bottom of the logarithm and the thing at the top of the logarithm to the same power, and it kind of preserves the value of the logarithm. So what we're going to do is we're going to say this is just log 4 2x plus y squared. And you can prove that this works with a change of base formula, but the whole point of using it is to omit the proof. And this equals log 4x squared plus xy plus 7y squared. And this becomes 4x squared plus y squared plus 4xy equals x squared plus xy plus 7y squared. This becomes negative 6y squared plus 3x squared plus 3xy equals 0, or x squared plus xy minus 2y squared equals 0. Now, in situations like these, it's always a good idea to factor the expression. And I'm going to leave this up for one more second just so you can read through what I've written. And yeah, it's gone now. So it's always good to see if you can factor the expression at hand. And this is kind of an easy expression to factor, because we see that if x equals y, we're good. So we know x minus y divides the expression. And then we can figure out what x minus y times what equals this expression. The first thing has to be x, and it's minus 2y squared. So it's probably plus 2y. Does this work out? X plus times 2y, it's 2xy, minus xy is xy. So all the terms work out. So this equals 0, which means x equals y, or x equals negative 2y. Now we're gonna use these two constraints on the second part of the problem, which said, for reference, that we're trying to find the product of all possible values of k, such that log 3x plus y equals log 9 3x squared plus 4xy plus ay squared. I hope this is legible. I will attempt to make it a little bit more legible for you. 3x squared plus 4xy. And we just plug in our cases. We have x equals y or x equals negative 2y. If x equals y, this becomes log 3 4x equals log 9, I think this is 7x squared plus kx squared. And again, we use our little trick that we introduced at the beginning. We can square the 3 and we can square the 4x. So this becomes log 9 16x squared equals log 9 7 plus k x squared. And the obvious solution here is that k equals 9. And we can make sure that we're not missing anything. And it doesn't seem that we are, because, I mean, the coefficients have to match, right? And we should definitely check that k equals 9 works, that we're not introducing any miscellaneous solutions, because although there is a methodical way to approach figuring out if you are going to introduce a miscellaneous solution or not, it's often not worth following this methodical manner. For example, you would have to look at each step and each manipulation that you did and see if you introduced any new solutions, and it's really not worth doing all that when you can just check it at the very end. Now, the second thing we got to check is x equals negative 2y. And in that case, we have log 3 negative 5y equals log 9 12y squared plus 4y squared plus ky squared. 12 plus k. Is this 12 plus k? No, it's 7 plus k. 7 plus ky squared. And this implies that, well, I'm not quite sure this is entirely correct, actually. Let's make sure we did everything right here. We get log 9. Yes, this becomes, since x is negative 2y, 12y squared, and this becomes minus 8y squared plus ky squared, where we just did x equals negative 2y. And this becomes, again, applying the same trick that we used and not applying this change of base formula. This is just log 9 25y squared. And this equals log 9 4 plus k y squared, or k equals 21. Turns out these both work, and our answer ends up being 189. And if we go to this next slide, we'll see that that's exactly what we have for 189. We'll see in the solution, the first line identity is just squaring the thing at the bottom and the thing at the top of the log, or taking square roots as it's described here. All right, now we have problem 6. And this is a different type of computational intensity. There's a few techniques we need to discuss. So what we're discussing here first is, so if you see that the absolute value of z equals 1, I hope you looked at the question as you can scroll back to check out the problem. You see that this is a constraint, and you also see powers of z. It's usually very useful to use the exponential notation for numbers. And I will briefly introduce Euler's formula here because it's really helpful, just a compact way to write numbers. It is saying that e to the I theta equals cosine theta plus I sine theta. And if you haven't learned much about these, they're really helpful. But the computational aspect of this is understanding that this is the best way to look at the problem instead of using a plus bi and saying that a squared plus b squared is 1. So we're going to let z equals e to the I theta. And the question says that z to the 6 factorial minus z to the 5 factorial is real, which means we have e to the I theta to the 720 minus e to the I theta to the 120 is real, or e to the 120 I theta e to the 600 I theta minus 1, and this is real. Now, what does it mean something is real? It means that, well, we're actually not going to look at it like this, because this is not a very helpful method of looking at it. Because when we say that it's real, right? If we say that this is real, it doesn't help too much to factor it, because then we have the product of two complex numbers, and we don't really know if that's real or not. But what we do know is we know the imaginary part of this, and we know the imaginary part of this. The imaginary part of this is just sine 720 theta, again from the description that e to the I theta equals cos theta plus I sine theta, and this is minus the sine 120 theta, which means this problem just reduces to finding the number of theta such that sine 720 theta equals sine 120 theta. Now there's two cases. Either these are the same angle, we'll look at a unit circle, either these are the same angle, or they are they're like pi, like one of them is like x and the other is pi minus x. Right. So what we have here is that if they're the same angle, then we say that 120 theta plus 2 pi k right, 120 theta plus 2 pi k equals 720 theta, which means we have that 600 theta equals 2 pi k, or that theta equals 300, theta equals pi over 300k. And there's 600 values of theta that satisfy this. It's in 0 to 2 pi, it'll be 0, it'll be pi over 300, it'll be pi over 600, it'll be pi over 300, pi over 300, pi over 300, 2 pi over 300, 3 pi over 300, all the way to 599 pi over 300, right? Because you go up to 2 pi, not up to 1. Now the second case is a bit trickier. What if one is pi minus the other? This means that 120 theta equals pi minus 720 theta, 840 theta minus, or 2 pi k. It doesn't exactly mean this actually, because it can mean a wider variety of things. This can be 120 theta is pi plus 2 pi k, because these are all values that equal pi, minus 720 theta, or 840 theta equals pi plus 2 pi k. Or that theta equals pi plus 2 pi k over 840 equals pi over 840 plus pi k over 420. And we'll call this theta 1 for cases 1, and this is theta 2 for cases 2. And in an attempt to reduce the clutter, we'll take out these. But remember, there's 600 cases. There's 600 cases. And we're just going to box this right here. So how many of these values are there? How many of there are pi over 840 plus pi k over 420 in 0 to 2 pi? It turns out there's exactly 840 of these, because there's pi over 840, 3 pi over 840, 5 pi over 840, and it goes all the way up to, I believe, 839 pi over 840. And you can tell there's 420 of these. You can tell there's more than this actually. It's not just up to 839. It's up to 1639 pi over 840. You see, I got tricked up again because I thought it only went up pi, but it actually goes up to 2 pi. And so you can tell that there is exactly 840 of these. And so you end up with 840 plus 600, 1440 solutions. and it asks you for the value mod 1000, so it ends up just being 440. And while the solution does omit the final modding, it is accurate. Now here's a problem that on the surface looks quite reasonable, but there is a large amount of bash associated with this problem. So let's check this problem out. We're trying to find the number of 4-element subsets with the property that two of them sum to 16 and 2 of them sum to 24. So there's really just 2 cases here. We have like A, B, C, D. Then either A plus B equals 16, C plus D equals 24, or there's some double dipping. So like A plus B equals 16, A plus C equals 24. This first case is actually quite easy to check out. We just go down the list of possible cases. So right now we're on what are we on? We're on A, B, C, D. These sum to 16, these sum to 24. So if AB is 115, then it's also worth noting that if these are separate, then this can be like 115 all the way down to 7, 8, because these are the number of unordered pairs that can sum to 16. There's 7 of them. Right. And for CD, this goes from 420 to, it goes all the way to 24, but it doesn't go all the way to 24 because we only count the unordered pairs. It goes all the way to 11, 13, which seems to be 8 cases, right? And you'll also note that there's no issue with it being like a 12-12 case because we conveniently stop at the halfway point. So there's 7 cases here and there's 8 cases here, and this would be if the two had nothing to do with one another, but they do have something to do with one another. So we can't just multiply these numbers together. You'll notice that if you have 115 here, you can't have a 1 or a 15 here, but 1 isn't in any of these sets either. Only 15 is. So if AB is 115, 15 can't be used. So you have 8 minus 1 cases that work. 15 is blocked. You have 2, 14, again have 8 minus 1 cases. 3, 13, you again have 8 minus 1 cases. And at 4, 12, notice that 4 can be used, but 4 is in the set. 12 can't be used. 12 is like a possible thing in this set too. So we counted that there's 8 possible C, D pairs, unordered pairs. So in these cases, like 1 could not infringe upon the possible things that will go in C, D, because 1 can't possibly be in the set. 2 can't possibly be in the set, but 4 can. So now we have to subtract 2 here. It's 8 minus 2. And it goes all the way to 5, 11. It's 8 minus 2. I'm just going to start saying 6. 6, 10. There's 6. And 7, 9. There's again 6. But there's one thing that's really important to check here, and that's that this 4, 12 case, yes, you can't, what can you do? You think that neither 4 nor 12, or you think that both 4 and 12 can show up, but actually in this case, 4 can show up, but 12 actually does not show up in any of these. You notice it only goes up to 11. So 12 does not appear in any of these. And so 12 is actually, it's not an issue. If you have 12 here, it can't possibly be in here anyway, so we don't care. So this is actually 8 minus 1. And so we end up getting, there's 4 7s, 4 times 7 plus 3 times 6. 18 plus 28, that's 46. So we have 46 cases here. So remember, in case 1, we had 46 cases. So I hope I've illustrated the way to go about this sort of issue here. We simply go through the possible cases for A and B, and then we see how that screws up with things in C and D, and we subtract off things that don't work out. Now, for sake of time, we will not go over the second case, because the second case goes much like the same as the first case. And we simply end up with 210 valid subsets that end up working out. Right, and that's exactly what this solution says. Now we're going to look at problem 12. So this is a late AIME question, and it's quite an interesting question. So it says we look at the numbers 1 through 18, and we just want to find the probability that a random subset, its elements sum, or its elements sum is divisible by 3. So we have 1 dot 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 18 random subset sum 3 divides the sum. So first of all, we're obviously not going to look at this in terms of a probability. We'll look at it in terms of the number of working cases over the number of unworking cases, because it's not immediately obvious how to attack this as a probability question rather than as two sort of counting questions. So the first thing we'll note is that whether or not you include a 0 is irrelevant, and that is the one thing that we will do that's related to that's directly related to sort of manipulations of the problem. So let's say you have like the number 3, right? If you include this number, it doesn't change the value of the sum mod 3. So it doesn't really matter if we include this number or not. And you can effectively say that this number is not even in the set. Why is it not in the set? Because let's say you have a subset 3 x, y, z, a, b, c. Some nonsense here. And we want this stuff to sum up to something that's divisible by 3. Well, the thing is, if you have this versus if you don't have this, x, y, z, a, b, c. And let's say you have a bunch of other subsets. So you have w, x, y, you have w, y, and then you also have like 3, w, x, y, 3, w, y. Well, let's say some of these work and some of them don't. So if, let's say like 2/3 of them work here, then 2/3 of them will work here, and we'll end up with 4 working out of 6, which is the same as the number that work if you just don't include the 3s. So in fact, we will not be including 3s, and also we will be replacing this 1 through 18 with just the values mod 3, because if you're finding the sum mod 3, then the only thing that matters is the values mod 3. So 1 dot 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 18 becomes 1, 2, and we don't count 3 because we don't care about 3. And then this is like 4 and 5. And then we again don't count 6 because it again does not matter, does not change the probability. And so we end up with 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. So our set effectively only has 12 things now. And we're going to say the number of like 1s is x, number of 2s is y. And the reason we're saying this is we're probably going to end up in a situation where we have to count like which 2s are we including in our set. And maybe if there's 2 2s, then we have to have 2 1s, so then the sum is 6. Or maybe have 5 1s. That's what we're thinking. So if the sum of the numbers is divisible by 3, what this means is that x plus 2y is going to 0 mod 3. And an interesting way of looking at this that will also appear on the AOP solution, so I'll simply explain it here, is that you can take this 2 and you can just take it mod 3. So you make it negative 1 y. So you have x plus negative 1 y 0 mod 3. Or x is congruent to y mod 3. And this really helps because this perspective that x is congruent to y mod 3 allows you to attack the problem in a very sophisticated manner. So remember, we have 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. We have 6 1s, 6 2s. And we are looking for subsets of, we're looking for subsets of size 4. Yeah. So we're really considering that the sum has to be divisible by 3. We have these 1s and 2s. And so we're going to consider the number of 1s and number of 2s we have. So let's say the number of 1s we have. Remember, x congruent to y mod 3. X is number 1s, y is number 2s. So let's say the number of 1s we have, 0s we have, no 1s. 1s we have is 0 mod 3. How many? So the number x is 0 mod 3. How many ways does this happen? Well, we can either pick 0 1s, that's 6 0, plus 3 1s, that's 6 3, plus 6 1s, that's 6 6. And the thing is, we can sort of consider these all as one case. This is just number of x's is 0 mod 3. This means the number of y's also has to be 0 mod 3, which means you multiply this by itself, or you simply square it. Then you can also do x is 1 mod 3. And this would be 6 1 plus 6 choose 4. And you'll multiply this by, well, we know x has to be equal to y mod 3. So the number of 1s. It's a bit of an interesting situation right here. Because if you have, we're really considering the cases number f based off the number of numbers that are 1 mod 3. And so if there's one number that's 1 mod 3, then we need 2 numbers. Or no, we simply need one number that's 1 mod 3. So if you have one number that's 1 mod 3, then we can have one number that's 2 mod 3. Ah, interesting. So this would be, if you square this, you'll end up getting 6 choose 1 plus 6 choose 4, which is 15 plus 6, 21 squared, which is 441. Oh, okay. Yeah. So if you have one number that's 1 mod 3 and you have another number that's 1 mod 3, then you'll simply square this as well. And if they're both 2 mod 3, it'll be 6 choose 2 plus 6 choose 5, which you'll note is again the same as this, because the 1 becomes the 5 and the 4 becomes the 2. And you'll note that this is almost identical to a solution on AOPS, except this solution is even more slick because all the terms are squared. And when you eventually end up calculating out the sum of squares, which is not that hard, we'll include the calculation just because it's a computational lecture. This is 1 plus 20 plus 1, which is 22 squared, plus 6 choose 2 is 15, plus 6 is 21 squared times 2. This is 882. 22 squared is 400. What is 22 squared? 22 squared is 4444 equals 484. 484, 6, 6, 12, 1366. And this is over 2 to the 12th because there's only 12 free digits here. These are the free digits. Remember, we don't care about the 0 and 3s because they perfectly cancel out. At the very end, we get 1366 over 2 to the 12th, and we're looking for the numerator of this value. That's what the problem ends up asking. And that's just 1366 over 2, which is 683. And this would be 683 over 2 to the 11th. And that's precisely what we'll end up finding here. It's simply 683. And finally, we'll be looking over problem 14. And problem 14 is precisely the type of problem that showed up on this year's AIME as well as problem number 12. Simply the sort of problem where you're moving around some sort of circle and there's some recursion involved. On this year's AIME, there was recursion involved as well. And this problem is truly quite nice because there's a lot of computation involved, making it a very apt choice for this lecture. But it's also, there's some symmetry involved, and you can miss it if you're not careful. So what this essentially says is, you got, what do you've got? You've got a heptagon, you've got, you have S, P1, P2, P3, E, P4, P5. This is your heptagon. You always label them counterclockwise or clockwise in this manner. You always label them in order. Right, so you're going to start here and you're trying to find the number of ways so you end up at E in no more than 12 jumps. So you're going to try to find the number of ways that you end up in E in 1 move, plus number of ways you end up in E in 2 moves, number of ways you end up in E in 12 moves. So here's how the problem really starts off. We can think of this as a recursive problem, right? But the first thing to notice before we think about any of that is that the frog here, let's say we call f of x number of ways to get from S to E in x moves, right? If the frog moves to P1, well, the situation is completely symmetric about P1 and S. So that means the number of f of, like if we say P5 of x is the number of ways to get from P5 to E in x moves, then P5 of x is equal to P2 of x, simply by symmetry. And similarly for P4 of x equals P3 of x. Because all of them are symmetric about E. So this will help us in our computation. But the most important part here is the efficiency of your recursion. So we're simply going to define 3 recursions. We're going to define, I'm going to call S of x the number of ways to get from S to E in x moves. And I'm going to call G of x number of ways to get from P1 to x to E in x moves. And I'm going to call F of x the number of ways to get from P2 to E, or this should be P2 and this should be P3 to E in x moves. Now note that before I had P1 to X, P1 to E in X moves. But this would be redundant because the number of ways to get from S to E in X moves is the same as the number of ways to get from P1 to E in X moves, simply due to symmetry. There's a symmetry along this line. All right, so now we're time to start figuring out what these recursions look like. And I'm telling you, the choice of these names is very helpful. In fact, it might even be worth labeling these points F and G, just because it really helps out the recursion. So, how many ways are there to get from S to E in X moves? Well, the recursion says it's a number of ways to get from P1 to E in X minus 1 moves, because you move one and then you get P1 to E, or from P5 to E in X minus 1 moves. And by symmetry, this means that S of X equals P1 to E is the same as S to E. S of X minus 1 plus, and P5 is symmetric to G, so plus G of X minus 1. And you'll see this all often. You could try to start filling this table in, but then you wouldn't know what G would be. So you'd have to find a recursion for G. G of X equals, so if you go this way, you get to this, which is symmetric to this. So S of X minus 1 plus, and if you go this way, now you're at F, so plus F of X minus 1. Lastly, what is F of X? And this is where you might have a bit of trouble if you don't have very much confidence in your ability to do some recursion. F of X, you don't actually take into account E. All you say is that F of X equals G of X minus 1. And you define F of 1 equals 1. Which means you sort of define G of 0 equals 1, which doesn't really make sense, but we don't really talk about this. Yes. And why do we define F of X as G of X minus 1? Well, because you never really get to E. E is like some sort of mysterious position that you don't even think about. So the only other place to go is to G. And remember, if you came to E at some point and X was not equal to 1, then you would be screwing up because you're not getting there in the right amount of moves. You need to get there in X moves, you got there in 1 move. Now, with these recursions in mind, we are going to do what many people have done, and many people have done on many problems. And it's quite a relaxing way of solving the problem. And it can help solving a wide variety of problems. You can do this with finite differences, simply build a recursive table, and then maybe do finite differences on each column of the table. You can do many things with tables such as these. I'm just going to write X, S of X, G of X, F of X. And we're just going to run down a long table. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the last tidbit of advice I have for you here is that you want to find a nice way to relate different columns of the row, because we do have these recursions, but what does this mean for this table? Well, I'll tell you what it means. It means that, and this is X, this is X. All right, brilliant. Right, so what this means is, what does S look like? Well, S simply looks like, if you're going to look at 2, right, it looks like you're going down from here and you're going down from here. You just take these two values and you add them up, and you get this value. And this is just saying S of X minus 1, which is this value, and G of X minus 1, which is this value. But this is helpful because it helps your brain think about how to fill this recursion in. Similarly, G of X is S of X minus 1 plus F of X minus 1. So if you're trying to find G of 4, take F of 3, and you take S of 3 and you take F of 3. And lastly, F is just G of X minus 1, so you simply go diagonal. So this is just a geometric representation of what you're doing in these recursions. And this is really going to help you fill it in. we defined like this is 0, 0, 1. This is 0, 1, 0 because we go this way. And filling in values, we end up getting, after quite a bit of time and computation, but not after difficult or even frustrating computation. This is not a square root. This is not anything like that. This is simply adding up numbers. And in slightly worse scenarios, you might find yourself having to multiply numbers, and that can get a bit tedious because if you have to repeatedly multiply numbers, there's a lot of opportunity for error. But I'm simply adding up numbers here. This is 19, 89, 66, 42. This becomes 66, 131, 155. And we just have to find how many ways are there to get from S to E in at most 12 ways. So that's in 1 way plus 2 ways plus 3 ways all the way down to 12 ways, which means I have to add up all these numbers and I've arrived at my answer. And I will skip this computation. The sum is 351. And that's our answer. This is the recursion. And this is the table, LaTeX, to view for your pleasure. Slightly a bit more organized than this table I've made, but they have the same values. I hope you learned a little bit about computational techniques and how to optimize your more bashy steps to make sure you don't make any silly mistakes. Thank you. Eli, you can stop.